So the title of today's presentation will be Building First-Class and Reusable Pipelines. So we all know that data and analytical pipeline is a crucial need for enterprises as it allows organizations to extract valuable insights from their data, which can inform business decisions and drive operational efficiencies. So when working with multiple data sources and multiple business process, the reusability of the pipeline is a critical consideration. So reusable pipeline allows organizations to build pipeline once and reuse it for multiple tasks rather than have to build multiple pipelines for multiple tasks. So this improves the efficiency of the development process and reduce the amount of code that need to be written and maintained. So additionally, reusable pipeline often easier to test and debug because there's just less code to review and fewer potential points of failure. So also it make it easier to add new features and make changes to pipeline. And there's a clear structure to follow and there are fewer dependencies to consider. So often in practice, we run into quick multiply of the number of pipeline we need to support. So if you have, for example, 5, 6 different variation of the data sources, each require slightly different processing, and you have like for example, 10 different special business process for each of these different pipelines that quickly multiple to 50 different pipeline configurations. So without reusability, the amount of work and code base you need to create in order to support these large number of different pipelines will quickly grow out of control. So the pipeline building has become an important category of software product of its own, with a number of products offering different features and capabilities. So here, Julius, how we differentiate from alternative solutions, really, we offer much greater reusability than the other available solution in the market. So in order to understand why we do better in reusability, we can take a look at the evolution of a programming language paradigm. So after all, pipeline building is a form of programming. There are valuable lessons we can learn from how different programming paradigm has evolved and how it affects code reusability. So here is a very high-level summary of how the different programming paradigm evolved and the key features that has been driven these evolutions. So overall, there is a clear trend of better code expressivity and reusability throughout the evolution of different programming paradigm. So let's examine some of the key innovations that has behind such improvements. So the first big innovation is parameterized functions. So before the invention of parameterized functions, developer only write code in assembler or machine code, so which are low level that are specific to a particular type of computer. So coding in assembler is clearly not reusable at all. It forces developers to repeat the same code multiple times for different tasks. This makes it difficult to write and maintain large complex programs. Parameterized functions, on the other hand, allow developer to implement a specific algorithm for specific data type only once. And whenever they encounter the same algorithms and the same data type, they can just call the existing function. This greatly improves the reusability of code and make it easier to write and maintain complex programs. So parameterized function, therefore, enables the new programming paradigm called structured programming. So the next big innovation in programming paradigm is polymorphism. So polymorphic function allow a specific algorithm to be written once and be used for different data types. So this is a clear improvement from the parameterized functions, which can only be applied to the same types. So the different types will have different behaviors. These special behaviors are captured by virtual functions or methods. So this is really the core idea of object-oriented programming. So this further improves the code reusability and allow the code to be more expressive. So now you can write the same algorithm once and apply that to different types. The next big evolution is called a function as a first-class citizen. So when functions are first-class citizen, it means that they can be parsed as arguments to other functions. They can be returned as a result from a function, and they can be stored in variables, just like any other value in your programming language. So this is a big deal because it allows developer to reuse code for different algorithms and types by passing functions as a parameter. So this is, again, is another improvement from polymorphic functions. Now you can write a generic code that works for different types as well as different algorithms. So for example, you can write a generic map reduce pattern and it can take in different map and reduce functions. So this map reduce algorithm can work for any map function or reduce function and work for any types. So this greatly improved again, improve the code reusability and make the code easier to share. So the first class function is really the defining feature of functional programming. So if you look at the evolution of the programming paradigm, clearly these are the key driving features that improve the reusability of the code, make the code more expressive, make the code more maintainable because you have fewer code to work with. So analogous to the evolution of programming paradigm, we can apply the same lesson to the pipeline building. To achieve maximum reusability of pipelines, the pipeline should have a standalone representation that is independent of the underlying code or tools that has been used to create them. So this is because the standalone representation allows pipeline to be directly shared, reused, modified, and combined without having to navigate through the underlying code or tools. So this greatly facilitates a much greater level of sharing and reusability. Additionally, the pipeline representation should support parameterization, especially polymorphic parameterization, allow the same pipeline representation to be used to create a different data and analytical processes depending on its parameters, just similar to how the object-oriented programming works. And lastly, the pipeline representation should be a first-class citizen. That means it can be passed as a parameter to another pipeline and create a sophisticated combination of pipelines. So all of these are really the lessons we have learned from reviewing the history of a programming paradigm. So with that, go ahead if
So
you
yeah,
have a
may I
question.
ask you a question? So here the polymorphism, that means that the parent classes and the inherited child classes, right? So what are those classes? Do you mean each pipeline step is kind of it's a class, or so probably it's not clear to me right now what this polymorphism refers to.
Yeah, it means your pipeline should have a representation. If you think in terms of maybe JSON, if some tools use JSON to represent pipeline, that is clearly not a sufficient enough representation to support the polymorphic parameterization
Okay.
because JSON cannot take parameters and the JSON doesn't understand the types. So therefore, this is generically talking that if you want to maximize your reusability, you need a representation of pipeline that can actually take parameters and understand the data types. So
Uh-huh.
later on, we go through a demo, you'll see how Julius does it. So right now, like there's no other tool that can offer such a flexibility
Yeah,
on the
so
market.
that's kind of my question. So what a polymorphism looks like and what a first class system looks like. So probably when you talk about the examples, you can show
Yeah,
it to me.
so
Thank
right
you.
now it's on the abstract, like a
Yeah,
philosophical level, and later on we're going to show examples how
yeah.
Julius will implement these
Thank you.
features. So yes, so with this like progression of features that gradually improve your reusability, we can examine where existing like pipeline building tools um, falls into by looking through this lens of programming paradigm. So many pipeline building tools such as Nime and Talent, they create a pipeline through drag and drop GUI. While this is indeed a standalone representation of your pipeline, but it doesn't support parameterization, means that multiple copies of the GUI pipeline must be created for different data sources and business processes, even though these data sources and business processes may largely share like pretty much the same logic with only slight tweaks from each other. But in that case, you have to create totally different copies of this GUI representation. It doesn't facilitate great reusability. So this is very similar to the paradigm of programming in assembler. There's very little sharing and reusability allowed in this type of tools. So another common approach is to use a SQL syntax to create a pipeline. So the best example are the BDT and AppSolver, for example. So while SQL is a standalone representation as well, we all know that SQL cannot take parameters, especially polymorphic parameterization. So this again results in poor reusability, very similar to the GUI-based tools. So therefore, duplicate the SQL script must be created and maintained for different for each of your different version or variation of the pipelines. So another very popular and common way to create pipeline is through programming APIs, such as Airflow, Dask, Ray, Prefect, Dexter, etc. So these tools are commonly based on Python programming language. So even though Python itself supports polymorphism and first-class functions, it doesn't mean that the resulting pipelines are polymorphic or first-class citizen. So this is an important distinction to make, because here we're talking about the sharing and reusability of pipelines, not functions. So therefore, the pipeline themselves need to be polymorphic and first-class citizen. So most of the Python-based tools do not support the standalone representation of pipelines that can be independently manipulated without going through the underlying code. So therefore, a developer has to change the underlying Python code in order to reuse and modify the behavior of pipelines, which is tedious, inefficient, and error-prone. So even for the few Python tools that do support a standalone representation, these representations are commonly in data format like a JSON or XML. So none of them support like a polymorphic parameterization. So if you want the pipeline to behave differently according to the type parameter that are being passed in, you don't have such flexibility using these tools. Also, none of them support the pipeline as a first-class citizen. So therefore, if you want to combine two pipelines together, that require heavy change in the code. You cannot just simply pass one pipeline to another as a parameter. So different Python-based tools, like they have a varying level of reusability, but generally they are similar. They fall between assembler and structured programming. None of them support polymorphic parameterization, and none of them support pipeline as first-class citizen. So this is really where Julius came in, and we want to build a very flexible and reusable pipeline tool that build the pipeline as a first-class citizen with full capability of polymorphic parameterization. So we can release the full power of reusability and make the pipeline building much more modular and also much more reusable. So this is a very high-level summary. So next, if there's any question, please feel free to ask. And then next, I'm going to go through a quick demo, show the main feature of the Julius, and also show some code and to walk through how we support polymorphic parameterization and how we pass pipeline as parameters. So here I'm going to just show a um, uh, practical example of how it works, how it looks like after the pipeline has been constructed. Then we can go back to look at the code and show how the how the how it is created through code. So this is a data processing and machine learning pipeline we built using Julius. So the application here is a credit card approval process. It's a couple that apply for a credit line increase. So here you can see that in this pipeline, we can click on any of the node to see the data from that point of the process. So in this case, you can see that the raw data is read from AWS um, bucket. So we support various data connectors to different data sources. And you can walk through the process to, for example, you can visualize the histogram of your raw data. And along this portion, it creates a additional feature engineering by adding additional columns. And then down here, it builds a decision tree machine learning model to forecast the default probability. And then in the end, it reports the performance of the machine learning model using, for example, ROC curve or like a Gini metrics. So here, like one of the, certainly, even though we have been talking about the reusability so far, but here, like I hope you can appreciate some of the other features we provide. One is a complete transparency and visibility to every step of the way. You can click on any of these pipeline and see what's the underlying data behind it, and you can pretty much read through your pipeline and see how the logic and data flows from beginning to end. And second feature I want to quickly mention that the pipeline, Julius pipeline, is automatically scaling. So here the different colored nodes represent the different physical machines. So this pipeline is executed by 4 different machines in parallel. So allow you to automatically take care of the parallel computing and get the great performance. So all of this is totally transparent to the developer. Developer doesn't have to write a single line of code to take to specify how the graph or how the pipeline will be distributed, or does it automatically. So these are the other two key feature I want to highlight. So and also in addition, we fully track the data lineage. So for example, if you want to look at any of the node, you can easily see how the upstream dependency it has in order to get this node. What are all the previous steps you need to go through in order to produce it, and also you can find all the dependencies that these nodes feed into, so that you have full transparency of your data dependency lineage, and also you have visibility to the data on each of the node, which make it very easy to debug and test. So, is there any questions so far at this point?
I have a question. So here, so for each node, right? So each node is a pipeline, is a pipeline step, right?
Yeah.
So this whole pipeline is a DAG. So in this visualization tool, so we can also access to the outputs of each pipeline step, right?
Yes.
Where are those? So you also mentioned that so this is a cluster, it's kind of elastic cluster, so it can so we can have more machines if necessary. So my question is, where are those results stored? Are they stored in the locally on those workers, or are they stored in a centralized place? And also, uh, if they are stored in a centralized place, do we do any versioning of those tools? And maybe another pattern that is very frequent is that so probably usually a pipeline is not data pipeline is not successful once, right? We have to, so it breaks at a certain point, and if we have to resume that. So is that possible? Okay, so that's multiple
Yeah,
questions.
it's
First
a
of all,
lot
is
of
that
questions, and thanks for asking that. So let me answer it one at a time. So
yeah,
here, all the intermediate results were stored in memory. So it
in
is
memory. Okay.
yeah, not stored in a central database because that will kill the performance. So basically, we leverage the distributed computing resources, and all the
Hmm.
intermediate results were stored on individual workers' memory. So you may worry about the availability, the size of the memory. So
Yeah.
far, we haven't run into a single case where we run out of memory, because nowadays the memory are cheap. We can easily connect dozens of machines or even hundreds of machines. Each could have a 64 or 128 gigabyte of memory. It's pretty much for all the problem we have seen. There's no problem to cache all the intermediate data in memory to make it easily accessible. These intermediate results are extremely valuable in terms of debugging, testing, and also understanding your entire process. To us, we definitely think that the cost to store these intermediate results is definitely worth the benefits. So therefore, certainly we can turn it off if you really run into a situation where your memory is constrained. We can turn off the caching, but for us, like it provides so much value for development and deployment and debugging. So by default, we turn it on. So to your second question, what happen if there's error and how do you recover from error? So that probably is a whole different topic. It's a like a very involved and complicated topic, but the short answer is we can snap the entire run into long-term storage. And also whenever there error occurs, we can have monitor and trigger to automatically handle the error by alerting developer or roll back to some kind of predefined values or strategy. So all of that we provide strong support. So yeah, that is a very short answer to that question. Is there more that I haven't answered?
Mm, probably is a follow-up question. So if the results they are stored in the memory, so because memory is not does not so data stored in memory does not persist, right? So a very common pattern is that we do some analysis one day, and maybe a few months later, then we present these results, say to FDA, and then we'll have to go back, and then FDA asks us some questions, and then we'll have to go back to trace, just figure out how this report was generated. So probably we will need the intermediate results materialized or persisted, just materialized in a hard drive like S3 or somewhere. So probably, yeah, this is my question
Yeah,
here.
definitely. So we actually support a very easy
Okay,
single
got
line
it.
of code to persist the entire distributed pipeline and all the intermediate data to your long-term storage. It could be S3 bucket, it could be a disk file system. That is
Okay,
very convenient if you
okay.
want to
I think
persist
that,
it.
yeah, got it,
Yeah.
got it. And all of the results, they are organized by pipeline rounds, right? By rounds.
Yeah, by runs, and you can persist any of the runs. And also, yeah, later on we're going to show that you can also turn this into like a in-memory database. You can actually query it because all the intermediate data are available in the memory.
Mm-hmm.
Once it's in memory, you can run arbitrary queries so that you may want to figure out certain dependencies that you haven't outputted during your run. You can run this query after the fact while the data is still in memory.
Okay, got it. Thanks.
Yeah.
Yeah.
Uh,
Any
in,
questions? Yeah. Okay.
okay. Yeah. So next, I'm going to quickly show how our syntax works in order to support the polymorphic first class pipeline. So here, sorry, forget to mention one thing. So here, just quickly, each of the node can call a function. So this function you can define yourself. For example, if you have a C++ or Python or Java library you want to reuse, you can easily plug in any of the function from this mainstream programming language into any of these nodes. So you don't have to rewrite your analytics library from scratch. You can totally just connect to them and reuse as part of the pipeline building process. So now let's go to the main themes on how let's probably increase the font a bit. I'm going to show some of the code so that to illustrate how we define the pipeline and why we construct it in a way that allow the pipeline to be first-class citizen and allow it to take a polymorphic parameterization. So here is our syntax to define any pipeline. So it's a domain-specific language. So this particular syntax, it's very easy to explain. This particular application is to build a Fibonacci sequence. I use it as a very basic example of pipeline building. So you can see that it is a declarative syntax. There's no intrinsic ordering. It doesn't execute from beginning to end. It just declarative like dictionary declarations. The main declaration that defines this Fibonacci sequence is this line. So basically, it says that so each declaration is a instruction to create a particular node. So in this case, it says if you want to create a node whose output is nth term of Fibonacci sequence, and this term is not an initial condition. So then I'm going to compute this node from the two previous terms. These two previous terms are also node themselves. So I can have the previous terms using the same parameterization, n-1 and n-2. These represent the two previous terms. And then I'm going to compute whether they are initial terms or not. So once we have this preceding dependent node, I'm going to take their value and I'm going to apply a particular function called weighted sum. So the detail of this function doesn't matter. There's a particular programming interface. You can write any function you want and plug it in here. So if you look at this, this is really the core syntax that you need, the only thing you need in order to define sophisticated pipelines. So basically, you declare the logic for every output node, what it needs as an input, as a preceding dependency, and what function you want to apply in order to produce it from the input. So here you can see we have multiple Fibonacci declarations. So these are the overloaded polymorphic behavior. So for example, in another declaration, we said if this is indeed a initial condition, instead of doing the summation, I'm just going to create a random vector of 10 to produce that as output. So in this case, it's slightly different from the classic Fibonacci sequence because here we're computing apply the Fibonacci-like operation on the vector of 10 instead of on the scalar, just to make it more interesting. And also we have two additional declarations that doesn't have a second parameter, which automatically just call the existing declaration, refer them using alias to the existing declaration, and automatically compute what the second parameter is. So once we have this declaration, we can create the pipeline by saying that I'm going to use this declaration to compute the Fibonacci term of 3.2. So the 3.2 can be mapped in this declaration. If it's a floating point number, I'm just going to apply the rule or declaration that is an integer that has integer parameter. So in this case, in order to create the pipeline, we just take the match this variable which represents the output node and recursively expand that into additional input, and in the end we fully construct this pipeline. So this is how the pipeline is constructed using Julius declaration and also using our like a graph engine we call to execute the pipeline. So here once the pipeline is created, we can look at its results. So again, like we go back to the same GUI where you can visualize each of the individual nodes. You can see that initially it has a random vector as input. Then each of the intermediate nodes are really created from recursive application of these declarations. So this is really how answer your achieving your earlier question, how we can support polymorphic parameterization. So in this case, for example, not only we support the polymorphic behavior for different types, we also support the polymorphic behavior for different values. So in this case, if you have depend on the value of the second parameter, you can do different things. So this makes the pipeline declaration extremely succinct and also make the pipeline itself super reusable. Another key point I want to make is this variable refers to a output node of the pipeline, but because of every node knows how to create itself. So this is also essentially a reference to an entire pipeline because this represents the entire graph uh, in order to create this final node. So this variable represents both a output node as well as the entire graph that you need to create that node. So the next feature I want to show is that this can be passed in as parameter to your rule declaration. So make it a high level, high order pipeline definition that can take another pipeline as a parameter. So in this case, for example, we're showing a uh, we're showing a streaming use case. So we can turn the sorry, I'm just going to skip a lot of the things. So in this part, we're turning the pipeline into a streaming use case and pipe through a large number of random number to it. And here I call your attention to this particular declaration. So this is a declaration of compute the rounding average of all the data points you have seen so far. So this declaration takes a node ref, which is really the variable type we have shown earlier, the ref type. So this represents the node and also entire pipeline to get to that point. So basically, this declaration is a generic declaration that takes the entire pipeline as a parameter. So basically, attach a node behind it to compute the rounding average when you run the streaming use case. So you can see how it looks like. So here we turned the pipeline into streaming, and we feed the random numbers through the initial pipeline. And this is the rounding average declaration we just shown, and this actually is attached to the entire pipeline up to this point and compute the rounding average of the Fibonacci 5. So in this case, you can see that rounding average is converging to number 5, which is the correct value for the fifth Fibonacci terms. So here, essentially, what we have done is we streamed the 20,000 random vectors through this pipeline, and we compute this average, essentially running a Monte Carlo simulation of a Fibonacci sequence, which is a very expensive and convoluted way to compute the Fibonacci sequence. But the point is to illustrate that we can easily turn a batch mode into stream mode, and also we can support the pipeline as a parameter. So this streaming average can be attached to any nodes. So you just need to declare it once, and it's fully reusable. You can attach to any other use case. You don't have to rebuild it again. So I know this is probably a lot to throw at you in a very short amount of time. So I want to take a pause to see if everything is clear and is any questions so far. Yeah, so if there's no question, I can quickly show one more example, which shows how scalable our pipeline is. So this is a use case of pricing like financial instruments. So we have a big portfolio of 100,000 trade, and we are building an entire pipeline to price each individual of them, individual trade of them. And this entire pipeline has more than a million nodes. So it's too big to show on a single page, but you can drill it down. And when you drill down, you can see again the step-by-step computation of each of the individual steps of this pipeline. And here you can see that it is split in this particular trade is priced by jointly running on 2 different machines. The entire process is again using 4 different computers to work together. So to create this very large pipeline, clearly it's impossible to do so using like a GUI or SQL-based tools. You really need the expressive power and also the reusable declarations like we have shown in order to create this very large pipeline. Otherwise, any other tool is not able to express this level of complexity with a reasonable amount of code. So in our implementation, this very large pipeline is declared using, we can view the underlying declaration using 69 lines of code, like earlier we have shown in the Fibonacci sequence use case. So we only need 69 of them to declare this sophisticated pipeline of more than 1 million nodes. This is because we fully we really drive the reusability and polymorphism, and also the high level pipeline logic, passing the entire pipeline as parameter, leveraging these powerful expressions to make it super easy to declare extremely complicated pipeline using very small amount of code. So this really, like, I want to show a more extreme example of how easy it is to declare really complicated pipeline by exploit the reusability to its maximum. So that is pretty much all the examples I want to show. So for the next 15 minutes, I can open it up for questions. If there's any question, I'd be more than happy to answer.
So any questions?
Yeah, I guess I have one.
Hey,
And
Luke.
I'm sure, and you mentioned that you can make the outputs of nodes persist if you want to. But since the default is this more memory-based storage, does that mean that do you think this tool is really more set up to run entire pipelines at once every time, rather than, for example, running like just small slices?
Right. Yes. That is a great question. Yeah, sorry, I wasn't very clear in the beginning. So by default, all the intermediate results are persisted in memory, but it doesn't mean that you cannot save it to long-term storage at a particular individual node level. So in the early example, we have shown that we can read from AWS S3 buckets, but also any of the node, you can easily just code a piece of Python code to store that result. If you want to persist that report into long-term storage, that can happen automatically. So it just when you want to persist the entire pipeline in one shot into long-term storage, you need to call a special function. But each of the node, you have full freedom to persist to make that decision at the individual node level. So maybe you want to run the entire process from reading from the database, transformation, machine learning, and you want to persist the final report to your S3 long-term storage. That can be totally incorporated as part of the logic. So every time you run, the final report will automatically persist. You don't lose that.
So Yadong, I think Luke's question. So Luke, do you mind if I just add something on top of your question?
Yeah, please.
Yeah. So probably just usually, so when we run a pipeline, so for various reasons, so the pipeline just breaks, probably just because the machine just dies, right? Machine dies, and then if those machines die, then do we lose the information? Do we lose the data? Because if materialization requires a manual, well, if it requires just explicit instruction, then because of this machine issue, then probably we lost those intermediate results. Look, is that what you're asking? Is that close to what you're asking?
Yeah, and also because like some of these transformations, I may only need to run the one time.
Mm-hmm.
They're more static, right? Whereas others are going to be variable and will want to run as pipelines more like consistently.
Yeah. So the short answer is that you have the full control on how you want to organize your pipeline. So certainly you have the freedom and the tools to break it into multiple stages. You can have, for example, your data processing as a stage that you only run it once, and the results being stored into long-term storage. Then later on, you can start a second pipeline that reading from these storage and kick off its process. So you can go use the declarations to define your pipeline into different stages. That is totally up to you. And also to chip in your question, so if there is a, for example, machine failure, of course, all the intermediate results in the memory will be lost. In that case, but it's very easy to recover and recompute them just by rerunning the pipeline from beginning to end, because all the intermediate results are computed from the previous previous inputs. And if you have, you can also build in version numbers into your runs. You can take a parameter, because that's where the parameterization becomes so convenient. The next time you run, you can pass a different parameter, so the result will never override your previous iteration of the runs. So having parameterization can allow you to express many of these complicated logic very easily, including error recovery and also error handling.
Thank you. Any other questions?
I guess I can ask another one.
Yeah.
I was a little confused about the last example. So why are there over 1 million nodes? Obviously, like some of them are redundant, right? They do the same things, but they have a different input or something. I didn't quite understand.
Yeah, so it's actually quite quite easy to understand, because when you have 100,000 trade, if on average you need to have like say 100 node to price a trade, or 10 node to price a trade. So then when you multiply that by 100,000 trades, that become roughly a million nodes. So this is because in the traditional programming language, you build a loop through your 100,000 trades. That doesn't increase your lines of code. But in the pipeline context, because pipeline doesn't support the loops, it cannot have cycles. So therefore, every intermediate step that used to be computed in the loop has to be expanded as part of the graph as individual nodes. So that's why it expands to 100,000 multiplied by by 10, that become roughly a million nodes.
So go ahead. Oh, so each node is actually for one trade. One trade is one.
So no, actually, each node
multiple.
could be a step in pricing the trade. So yeah, if I can just quickly show the screen. So somehow I'm not able to share.
Oh, you cannot share?
Maybe it's my losing. But anyway, so there are 100,000 nodes in the graph. Okay, so now I can share. So in this particular example, for example, this node represents the trade. So this node, sorry, actually got the wrong one. So this is all the steps that goes into price one trade. It takes 82 steps to price it, but there are a lot of common nodes between trades. So when you have two trades that have similar, for example, cash flows or dates or day counts, they just share the same node. So therefore, on average, each additional trade add 10 more nodes to the graph, which are unique node to this trade on average. So that's why like we created only 1 million nodes for 100,000 trade. If you think about it, that is extremely efficient, because if you compute them on a standalone basis for each of trade, you would have to go through 82 of these nodes. But when you compute them in one shot in a big pipeline, big graph pipeline, you actually only need to do like 1/8 of the work, because many of the nodes are common for multiple trades. So this deduplication is fully automatic. So they are automatically detected for common nodes, and it's only computed once.
Actually, I have a question. So in one of your slides, or in one of the demo, I think you showed a Jupyter notebook. I think that's and it's pretty, in your demo, that's part of a report. Is that correct? So
So Jupyter Notebook is how a developer can interact with the system. You
Yeah.
can use your favorite IDE like VS Code or Jupyter Notebook. I personally like to use the Jupyter Notebook, just like many other data scientists.
Yeah. So yeah, Jupyter. So yeah, just we also like Jupyter Notebook because usually it just do something and also automatically generates a report, right? So what you showed in your demo, it's from the I think it's more like a report, just like R, what's it, R Markdown or Jupyter, so
Yeah.
something like that.
So this is really both the code and Markdown, so that it's really a tutorial. Oh, by the way,
Yeah.
anyone can just log into our like a free developer environment. If you're interested in how it works, you can just sign up for a free account and try it out. So basically, when you log in, this will be the environment you'll be entering into. So you have the entire like a Jupyter lab. You can play with any of these tutorials to look at our syntax, to try a few pipeline building yourself, and to get your hands dirty and play with it to see how it works. So I'm going to type the URL into the chat so that if you're curious, you can feel free to sign up.
I'm great, thank you.
Yeah, just click on that URL. It will bring you to our sign up page, and you can register for our. Yeah, if you click on that, you'll be entering into this online environment.
Okay, I will put that on our conference page just in case anybody wants to play with it.
Yeah, I know we are only 5 minutes left. I don't know if there are any more questions. If not, like always, I'm more than happy to answer questions via emails. Feel free to reach out to me if you have any questions, further questions.
Okay, no more questions? Okay, if no more questions, yeah, then thank you very much, Yadong. Yeah.
Thank you,
probably
Keeping, for having me here.
Yeah, and thank you for everyone for coming here. So that's a really, really interesting talk. Yeah, thank you very much.
Bye-bye.
Yeah.